in the last class we looked at the list ADT and we talked about a generic list ADT where we said insert any element anywhere, and then we talked about two other flavors of the list ADT. One is the stack LIFO, last in first out, and the other is the FIFO, which is the first in first out, or the QADT. Now, the generic list ADT, what did it consist of? It consisted of a sequence of items. Okay. So, it had a set of elements, and if you want, you could have completely an unordered set of items as in a generic list, or in the last in first out of the stack ADT, you had a particular flavor where you said you could only insert at the top and delete from the top. And in the first in first out, which is the QADT, we inserted at the end and we deleted from the first. So, it is like when you look at the generic ADT, it is like a vanilla ice cream, and whereas the stack ADT is like chocolate, and if you like chocolate, then it is like chocolate ADT, which does something very special and on the list ADT. And the first in first out is perhaps like butterscotch, which does something else special. So, depending upon what you like, I know these are some of the most favored flavors in ice creams. So, it is something like that. Okay. So, either a stack or a queue still qualifies as a generic list. Now, there is one problem with the stack or the queue, and the problem is the following. What we see is that whether directly or indirectly, there is some kind of ordering in the list. Okay. The items either are pushed onto the stack and popped from the stack in one end, or they are pushed at one end, removed from the other end, as in the QADT. Now, today what I want to talk about is, let us say I want to represent the family tree. Okay. Suppose I want to represent my family tree. Let us say A is a parent, has okay, the E a set of children. Let me say that P are the parents, does not matter whether mother or father, and let us say you have 4 children and these are your siblings. Now, this is clearly the older generation, and this generation now, for example, generally has the generation 1 above you guys has had perhaps only 2 children, F and so on. And suppose you want to find out who is the grandparent of whom and so on. Then if you want to traverse, if you had to represented all of this using a list, then the problem would have been, this would have been number 1 in your list, 2, 3, 4, 5, 6, 7, 8, 9, assuming that 6 came after 5, you have to put them in this particular list, and to access an element at 10, let us say, or to access the element, the 11th element for that matter, you would have had to go to the end of the list. Okay. So, this would have, but at the same time, the reason why I am talking about this is, when I am using a list to represent something like this, then what kind of a list will I use? I will use a generic list, because there is nothing like, when you look at siblings for example, there is nothing like a priority of one sibling over the other, but just the representation by itself, because whoever came first you put them in and so on and so forth. But deletion, for example, somebody dies in the family, it can happen at any point in the list, and almost all operations will become very expensive, okay, because you have to traverse mostly the entire list. So, the idea is, can we represent these kind of structures in a better way? Okay. So, one of the most popular representations, what do we want from this? If I want to access the j, the node corresponding to j, then I would like some information, right. What would I like to say? I want to look at the, then I would like J to say who is his or her parent, who is this one's parent, who is this one's parent if I want to find a lineage of J. Okay. So, how easy or how difficult is this depends upon the kind of representation that we are going to use. So, a tree data structure kind of suits this kind of data very well. Okay. So, what we are going to talk about is we are going to talk about a general tree, something like this, and then as I already said, the major objective is to be able to traverse this particular tree, see if a particular element is present in the tree based on certain criteria that can be satisfied and so on. Okay. We will come back after we do all this to the general tree, but this is in general a tree. Now, representation of the tree can be done in a number of ways. You can use an array representation, or you can use what is called, any general tree is represented by what is called the leftmost child right sibling representation. What this means is P, A, B, C, D is the representation for this, and this is represented like this, and we have I, which is represented like this. Then, sorry, this has two children, F, and this one has a leftmost child, J. I will explain in a minute what this representation is all about. Okay. Yeah. So, what is done is, notice that we take this particular tree over here and convert it to this format. What would I do if I was representing an array? I would say here 0, this is P. Let us say this node corresponds to P, and I will keep some information 0 over here. Then the indices go from 1 to 2, I would say A comma 1, B comma 1, C comma 1, D comma 1, and I would say E comma 2, F comma 2, G comma 3. I will tell you in a minute what I am representing over here, H comma 3, and I comma 6, and J comma 7. What I am storing here, if I am, this is an array implementation, and this is a linked list implementation. What is a linked list now? It is a recursive data structure. What is the problem with this tree? If I want to represent this tree, then using a linked list, then at every node I must be able to say, if I was representing it by the number of pointers, I must say that node has some max number of pointers n. To avoid that, I could have a list of elements on the other hand. That is exactly what we are doing over here. So, if you look at it over here, what is it that we are doing? We are saying here P is a root node and it has children A, B, C, D. Okay? Let us say A is the leftmost child or the oldest child. Then to make our representation more convenient, if this is the root node, within that it has a pointer to the leftmost child, which whose right sibling point to all the other nodes. And similarly, it will also have a pointer to its leftmost child. So, the tree is like this. Okay. The pointers are all pointing forward. On the other hand, in the array implementation, why are we doing this? Because I said one of the fundamental problems is we want parent information, or from the parent I would like to go to the child. One of these two information is required. So, if you look at this, the array implementation on the other hand, what do? We say that I store the parent in this particular, let me call it, the index of the node is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. Suppose I was storing it in an array. Then what we do is, we store a pointer to the node's parent, and now I have put the index 0. Index 0 means what? This particular node is the root node, all right. Next what I do is the element A. Now, element A is stored here, and who is its parent? Its parent is P, whose index is 1. Similarly, the node B is stored in index 3 and its parent is in node 1, and I keep that index. Now, for C what happens? A, B, C, D is like that. When I come to E, what do? I keep the index of its parent, which is 2, because A is the parent of E, therefore, I store E and 2 over here. Similarly, for F what do? I store F and 2 over here, okay, because for F the parent is again A. So, you repeat like this and you can use the array representation for any general tree. Okay. In the linked list representation, this representation is basically, this is array representation where we use pointers to the parent, in every node. Okay. On the other hand, in the linked list representation, what does every node have? Every node has a pointer to its leftmost child and the right sibling. So, notice that P is the parent, right, it is the root of this particular tree, therefore, it has only pointer to its leftmost child, its right sibling is pointing to null because the root has no siblings. Okay. And here what is it that is happening here? A is the leftmost child and it is pointing to its right sibling, this is right sibling, this is his leftmost child, right sibling pointer, leftmost child, right sibling, leftmost child, leftmost child, right sibling, leftmost child, right sibling. So, what have I done now? In all the arrows now, I have put the which corresponds to the pointer, which corresponds to that of the leftmost child and right sibling, RS. Okay. This is leftmost child and right sibling. Okay. So, we make these pointers like this. Now, that means what is nice about the structure? In every node, we are having only 2 pointers, the leftmost child and the right sibling. Okay. But so, basically you have 2 pointers in every node, but you are able to represent any general tree. Okay. Now, this tree is useful if you want to look at any arbitrary tree. For the time being, we will kind of postpone this and we will talk about this a little later, but remember that this is one such representation of a tree. What is the meaning of the leftmost child? Leftmost child is oldest sibling and oldest child, and the right sibling corresponds to its next sibling at that particular level. We will come back to this tree a little later, where we have either array representation or this. What we will look at is, we look at some special trees today. In particular, we will look at the binary tree. Okay. What is a binary tree now? Here is an example where we have the root and it also has 2 pointers, one to the left child and the right child. There is no hierarchy here, that is the fundamental difference. It is similar to this, where you have a node has 2 pointers, leftmost child and right sibling. The difference between the binary tree node and the general tree node is that the left child and right child, there is no hierarchy. What do we mean by that? Here A points to B, to a node at the same level, whereas the leftmost child points to a node at the one level lower. Okay. So, basically what we are talking about here is one level higher, sorry, or here on the other hand we are saying leftmost child and right child, left child and right child are at the same level. Now, what is the use of such trees? We will see in a minute. Now, how do you define a binary tree? A binary tree is defined like this. What is it? It is a finite set of nodes that is either empty or consists of a root and two disjoint binary trees called the left and right subtrees. Okay. What is it telling me? That this is a binary tree, it can also be empty and it has left and right subtrees which are again binary trees. Again going back to this example, if you started from this node, this is a tree still and this is also a tree, this is also a tree, it has only one node. But basically what we are saying is at every level the same structure follows again from every node, leftmost child, right sibling, that is what we said. Similarly, in the binary tree here also every node can have optionally two subtrees, it can also have one of the subtrees or it need not have any subtree at all. If it does not have the root, even an empty tree is a binary tree. Okay. All right. So, this is a skewed binary tree, the picture is given here in the slide. Skewed means it is skewed to the left, and then I have drawn another binary tree which is called a full binary tree. The nodes are full like this. Then you also have another variant of it called the complete binary tree. We will come back to this. What we mean by this is when you fill this tree, for example, notice that I have filled the nodes at the first level, nodes at the second level, nodes at the third level. When I am filling them, I go from left to right. Okay. This is a complete binary tree, while this one is not. This is not a complete binary tree. While its mirror image, this is a complete binary tree. Such binary trees have lot of applications in building what are called priority queues. We will talk about that a little later. Now, first let us see why do we want a binary tree in the first place, and is there any use of this? Okay. And what are the operations that you will perform on a binary tree? So, you need something. So, what is it that we do? These are the, so now what is the binary tree now? The binary tree is also an abstract data type, like we saw the stacks, queues and lists, or lists, queues and stacks. And so you have we have the binary tree ADT and abstract data type. Therefore, you have a representation. The representation says there is a root node and there is a left child and a right child. Okay? That is the representation. Binary tree node. So, essentially a recursive data structure, and then you have operations which can be performed. And what are the operations that you perform? Because an ADT is like a mathematical model and we perform various operations on it. So, what do you want to do? You want to create a binary tree. First, create an empty binary tree or create a binary tree with a particular node, because you have to start from somewhere. Then you want to find left child or right subtree. Okay. Then you want to find the parent of a given node, and right child, left child I already talked about. of course, we need a create empty tree always, that is required, parent, and not always, sometimes they ask for the root of the tree. So, creation of empty tree and sometimes a get root. This is not good to have, but since some of the books talk about it, I kept this particular operation, because get root, if you have, it tells you what the implementation of the binary tree is. Okay. So, now what we will do is, we will take one application, there are lots of applications of binary trees, can represent sets, you can do Huffman coding, you can represent heaps and dictionaries.